There is a new form of recreation that has taken water sports by storm. They've been very popular among, and you may have seen while you're at the beach getting that suntan. It is a simple yet fascinating piece of technology that has often been misunderstood. The science behind hydrofoils isn't complicated, but it is often misunderstood. The information found online isn't credible, so this video is a simple summary of the concept of hydrofoils, especially their kinematics and fluid mechanics. A hydrofoil craft is typically made up of three parts: an underwater wing, which is similar to an airplane wing but is optimized for water, a payload at the top, which could be a surfboard, boat hull, or anything that can be lifted out of the water, and a fuselage that mechanically connects the wing to the payload. Before delving into the complexities of hydrofoil technology, it is necessary to understand how conventional boats operate. Any type of watercraft uses three forces: a force that holds everything together and keeps it from sinking, a thrust that propels the craft forward, and a resistance force created by the friction caused by moving through the water. Hydrofoils use the principles of fluid dynamics to achieve lift and reduce drag. The shape of a hydrofoil is designed to create a pressure difference between the upper and lower sides of the foil. This pressure difference results in a net upward force called lift, which lifts the foil out of the water as it moves forward. At the same time, the friction between water and the surface of the foil creates a rearward force called drag, which opposes the forward motion of the foil. By minimizing drag and maximizing lift, hydrofoils are able to travel through water with greater speed and efficiency than conventional boats. This is why hydrofoils are commonly used in high-speed watercraft such as racing boats, ferries, and military vessels. A conventional boat is supported by buoyancy, propelled forward by thrust from an engine, a sail, or some form of human propulsion, and resistance is created by plowing water out of the way at low speeds or skimming over the surface of water at high speeds. A boat's weight is equal to the buoyancy force it generates, and its thrust is equal to the resistance it generates when it's in equilibrium. To go faster, one would need to increase thrust or decrease resistance. Buoyancy is the ability of a boat to float in water. It's determined by the weight of the boat and the amount of water it displaces or pushes aside. The displacement of water creates an upward force called buoyancy that helps keep the boat afloat. Stability is the boat's ability to remain upright and not capsize. There are two types of stability: static stability and dynamic stability. Static stability refers to the boat's ability to return to its upright position after being tilted. Dynamic stability refers to the boat's ability to remain stable while in motion. Drag is the resistance that a boat encounters as it moves through the water. It is caused by the friction between the water and the boat's hull and can be reduced by designing a streamlined hull shape and using a smooth paint finish. Propulsion is the force that moves the boat forward. It's usually provided by a motor, sails, or oars. The propulsion system must overcome the drag force to maintain forward momentum. In addition to these factors, other important aspects of boat physics include the effect of waves and wind on the vessel, the interaction between the hull and the water surface, and the design and placement of hydrofoils and other lifting devices that can improve performances and efficiency. A hydrofoil's underwater wing generates an upward force that lifts the payload above the water's surface. This significantly reduces the craft's hydrodynamic resistance because of the payload no longer generates divergent or transverse waves, and the friction produced between the craft and the water is almost eliminated because the wetted surface area becomes small. The upper lift is produced by deflecting water downward efficiently, resulting in an equal and opposite force upward. In theory, this is similar to how a drone flies by accelerating air downward. In conclusion, hydrofoils have an underwater wing that efficiently deflects water downward, lifts the payload above the water to eliminate waves, and reduces friction to allow the craft to travel faster. To understand that, we need to examine water closely and how it behaves. Water is a liquid composed of a sea of small molecules that are closely packed together. In a liquid, these molecules are free to move around while rubbing against each other and colliding into each other like individual cars flowing in a sea of rush hour traffic. Unlike a solid, where molecules are locked in place, water molecules can move freely. In gases, neighboring molecules can get farther apart and closer together, but in liquids like water, the molecules stay more or less the same distance apart, held together by intermolecular bonds. The sum of these forces divided by the area on which they're applied is called the pressure. It's essential to note that the water pressure can never be negative, but areas with higher or lower pressure can exist. Because water molecules can move freely and they experience forces from neighbors on all six sides, water, like all liquids, cannot maintain its shape and will fill the space it is provided. When considering the movement of water around a hydrofoil, it's important to note that the water pressure is different on both sides. This creates an upward force on the foil known as lift, which is a combination of two components: lift and drag. Lift is the force that acts upward and is perpendicular to the direction of the flow. It results from the difference in pressure between the upper and lower sides of the foil. The difference in pressure is caused by the curved upper surface of the foil, which makes water molecules flowing over it travel a greater distance than those flowing underneath the flat lower surface. The lower pressure on the upper side of the foil creates creates an upward force, which is the lift. On the other hand, drag is the force that acts forward and parallel to the direction of flow. It's created by the friction between the water and the surface of the foil. The friction creates a rearward force on the foil, which is the drag. The boundary layer of slow-moving water molecules close to the surface of the foil experiences high levels of friction, causing drag. The lift and drag components of the upward force created by the foil are what allow a hydrofoil to lift a payload out of the water and reduce the hydrodynamic resistance. As the payload is lifted out of the water, it no longer creates divergent or transverse waves, which reduces the hydrodynamic resistance substantially. This in turn reduces the amount of energy required to move the craft forward, allowing it to go faster. In summary, hydrofoils work by creating an upward force that lifts the payload out of the water, reducing the hydrodynamic resistance and allowing the craft to go faster. This upward force is created by the underwater wing of the hydrofoil, which efficiently deflects water downward, resulting in an equal and opposite force upward. The lift and drag components of the upward force are what allow a hydrofoil to reduce the hydrodynamic resistance and lift the payload out of the water. Understanding the science behind hydrofoils is fascinating and can help us appreciate the engineering marvels that allow us to fly over the surface of water. Boats and hydrofoils both rely on the principles of buoyancy and fluid dynamics to stay afloat and move through the water. Both boats and hydrofoils use the shape and design of the hull or foil to generate lift and reduce drag. They both have to deal with forces such as lift and drag, which can affect their speed and maneuverability in the water. Additionally, both boats and hydrofoils must be designed to withstand the forces of waves and currents and to maintain stability in different water conditions. Finally, both boats and hydrofoils require power, either from sails, engines, or other propulsion systems, to move through the water. Now that you're ready for hydrofoiling, here are some extra tips that you should know before you pick up a board. If you're new to the sport, a larger foil surface area will give you more stability, but then if you want to move like a jagger, then a smaller surface area of the foil is a better option. For the same reason, the shorter mast lengths provide stability, while a longer one lets you glide longer and help you maneuver better. A shorter foil wingspan offers maneuverability. We hope this video has provided you with a deeper understanding of the importance of composite materials in the world of engineering and design. Thank you for watching, and make sure to hit that subscribe button for more informative videos like this.